Good day, guys. So in this session, we are going to discuss the topic of limits. And we're not going to go too much into limits. We're just going to cover what's necessary to facilitate our study of derivatives. Okay, we're going to study what's necessary to facilitate our study of derivatives. So let's start with this discussion on limits, discussing limits. So I'll put here as a heading, I'll put limits. We're discussing limits. That's what we're discussing. So now we're going to start with an example. Okay. We're going to start with an example, and we're going to use this example to discuss or to kick off our discussion on limits. Suppose that we have the following function. Okay. So I'm going to say let f of x, this is our function f of x. So let f of x be equal to the following function. So we've got x squared, that's x squared. Let me write that again. The x must look like an x. So this is x squared minus x, so we minus x plus 2 plus 2. So that's our function. So let f of x be equal to this function. And suppose that we want to find the limit of this function. And we want to find the limit of this function. But first, let me just sketch it. I'm just going to draw a rough sketch of this function. So let me draw a rough sketch of this function on the xy plane. Let me do that again because it looks a bit skewed. Okay, so that's the y-axis, and this over here is the x-axis. So let me sketch this function. I'm sketching this function. Looks something like this. Okay, just a rough sketch of this function, and the equation of this sketch. This is a graph, the graph of the function. The equation of this graph is y is equal to f of x, where of course f of x is equal to x squared minus x plus 2. So this is what we are. So now this is what we have. And suppose that I want to find okay, so suppose that this is 2 here. Suppose that 2 is here. And suppose that I want to find the limit of the function. I want to find the limit of the function when the x values approach 2 from the left. So this arrow is showing, that's what this arrow is showing. This arrow is showing our x values approaching the number 2 from the left. So suppose that's what I want to do. Okay, so the way I write this is in the following way. I say, what is the limit? I want the limit, and I want the limit of my function x squared minus x plus 2 as x is approaching 2 from the left. Now, the way I show from the left, the way I indicate from the left is by putting a minus sign on top here, on the top right of 2. If I put a minus sign on the top right of 2, what I'm saying is I'm finding the limit of the function x squared minus x plus 2 as the x values are approaching the number 2 from the left side. And that's what my arrow here is showing. The x values are approaching the number 2 from the left side. So what exactly is my function approaching? Or yes, what is my function approaching? What exactly is this is supposed to be a straight line. Okay, let me just draw this dotted line. It's a dotted straight line from 2 all the way to the function or to the graph of the function. So that's what we have here. And another horizontal line that goes from, okay, that's a bad line. Let me do that line again. Okay, so what is it? I'm going to draw a line here. Horizontal line. Yeah, just think of this as a horizontal line. It's skewed. It's skewed, but it's basically a horizontal line. It's a horizontal dotted line. Again, we are finding the limit of the function x squared minus x plus 2 when the x values are approaching 2 from the left. That's what we're doing here. So how do you find this limit? How do you find it? Well, we can use a table to find the limit of this function when the x values are approaching 2 from the left. We can use a table. We can use a table. And how do we use the table? What do we do? Okay, let's go to the next page to show this. So a table that we use, it looks like this. Okay, you draw this table. You just draw a table that looks like this. It's got two columns, and the first column is for the x values, and the second column is for the function values, the corresponding function values. So the x values we choose, we're going to choose x values that are we're going to choose x values that are close to 2. Okay, let's go to the previous page again. We choose x values that are close to 2 from the left. Okay, because the x values are approaching the number 2 from the left. So we use x values that are close to 2 from the left. You see? So and we choose them such that the next number, the next x value we choose is even closer to 2 than the previous number. So, and in that way, we get closer and closer to 2, but we do not get to 2. We don't use the number 2. We just choose numbers that are closer and closer to 2, but never really get there. And that is sufficient for us to determine the limit of this function as the x values are approaching 2 from the left. So let's go and see then how this works. So let's start, we can start with the number. So which number can we choose that is close to 2? We can choose any number. But for example, we can choose the number 1. The number 1 is not that close to 2, but it's to the left of 2. Okay, or you can choose the number that's even closer to 2. But let's start with 1. Okay, we can start with 1 if you want. Number 1. If we choose the number 1 and we substitute the number 1 into the function, we get the number 2. All right. So we're starting. We don't know yet where this is going. We don't know yet what value the function will approach as the x values approach 2 from the left. So we choose the first number from the left, which is 1. And the next number we choose is going to be even closer to 2 than 1. And it's going to be, we can choose any number, but let's choose 1.5. Okay, let's choose 1.5. And you make a choice. You're the one who chooses what number to use. But you must just make sure that the next number is even closer to 2 than the previous number. So you're getting closer and closer. So now we choose 1.5. And what does 1.5 give us? It gives us 2.75. Okay. We don't know yet what number we're approaching, so let's keep getting closer so we can see. Let's choose 1.8. It's even closer to 2, so let's choose 1.8. And the corresponding value of the function for 1.8 is 3.44. It's 3.44. It's 3.44. We're getting closer now to 2. And still, we're not sure yet what the function is approaching. So let's continue. Like, we can't say what number f of x is approaching. So we have to keep going. Let's now choose 1.9. Let's choose 1.9. 1.9 is even closer to 2 than 1.8. So let's see what it gives. 1.9 gives 3.71. 3.71. Okay. Okay. Again, we don't know yet what number the function is approaching. So we're going to keep getting closer to 2 from the left. So we're going to choose 1.95. 1.95 gives us 3.8525. It gives us 3.8. 3.85. It gives us 3.8525. 3.8525. Again, we're not sure yet, but we keep saying 3. So we're not sure, is it 3? Is it approaching 3? But it's 3 points, but we had 3.44, and now we have, and we had 3.71, now we have 3.8. It looks like it's it's 3 point something, and it looks like it's getting bigger, but we're still not sure what it's approaching. But it could be approaching 4. It could be approaching 4, but we want to make sure of this. So let's choose 1.995, 995, and see what the function is doing for 1.995. And we get 3.985. We get 3.98, 985025. And it looks like the function is approaching 4. Okay, but we are not yet convinced. So let's try again a number that's even closer than 1.995. Let's try 1.999 and see what it gives. And it gives 3.997, 997, 001. So now we can see that on the right side of this table, which is on the right column, with the function values, we can see now that we had 3.985025. Now we have 3.997001. It looks like if we continue, what we can do, we can continue with this. We can check what it gives us for 1.9999. We can keep on increasing the nines to make sure that we get the right answer. So if we keep increasing the nines, we'll find that we also have a situation that where the function is also the nines after the decimal. We're going to have 3.999. Sorry, let me just fix this. Sorry, guys, just give me a second there. Okay, guys, as I was saying, so if we increase the nines on the left after the 1, so if we go 1.9999, we see that also the nines on the right increase. We get 3.999. Now there's 3 nines with a 7, with a 0001. So you see that what it basically looks like, or we can see clearly that as we get closer and closer to 2, as the x values get closer and closer to 2, because we don't get to 2, we get closer and closer to 2, and we're doing it from the left. So these numbers are getting closer and closer to 2. They're approaching 2. We can see clearly that when the x values approach 2, the function values basically are approaching 4. They also don't get to 4, but we can see clearly that these values of the function basically are approaching 4. So that's the limit. That's how you use the table to determine the limit. We can see clearly. So therefore, the limit of this function, x squared minus x plus 2, when x squared minus, the limit of x squared minus x plus 2, when x approaches 2 from the left, is simply just equal to 4. It's 4. It's equal to 4. So that's what it is. And what we call this limit the left-hand limit. So if we are approaching a number from the left, we call this limit the left-hand limit. Okay, so let me just put an arrow here. I'm going to put an arrow. Or let me not put an arrow. Let me just say it. Let me just write it. This is called the left-hand limit. So this here is called, the left hand limit. This is called the left hand limit. Okay, this is called the left hand limit. This is called the left hand limit because your x values are approaching the number from the left. And we also, similarly, we also have a right hand limit. So now if I ask the question, what is the limit of the same function when the x values are now approaching the number 2, when the x values are approaching the number 2, now from the right? Okay, what is the limit? If I ask the question, what is the limit of the same function when the x values are approaching the number 2, now from the right? Okay, so the way you write this is the following. Let's go to the next page. Now we want to find the limit of the function x squared minus x plus 2. And we find this limit when x is approaching the number 2 from the right. To show or to indicate that it's approaching from the right, we put a plus sign over here. We put a plus sign at the top right of 2 to show that the function, the x values are now approaching the number 2 from the right. So what does the table for this one look like? The table for this, again, you draw a table. Draw a table. The left column is for the x values. The right column is for the function values. And now this time you choose x values that are to the right of 2. And you keep getting closer and closer to 2 from the right. So we can start then with, let's start with 2. I'm sorry, not 2. We are approaching 2. So we can't start with 2. We don't, we are approaching 2. Let's start with 3. So if we start with 3, what's the corresponding value for the function when x is 3? It's 8. All right, so we don't yet see, obviously. We're still starting, so we don't see what the function is approaching. So let's keep getting closer. Let's choose 2.5. And for 2.5, we see that we get 5.75, right? Okay, still don't know what's happening. So let's get closer even. Let's get even closer, 2.2. And we get now 4.64. 4.64. Okay, we keep getting closer. We got 2.1. And we get even closer. We get 2.1. X is 2.1. Let's see what that gives. It gives 4.31. 4.31. Okay, we're still not sure. So we keep getting closer. Okay, let's choose 2.05. What does that give? 2.05 gives 4.1525. 4.1525. That's what it gives. Okay, still, but we just keep seeing 4 all the time. So we can already see that, okay, it's approaching 4, but we need to be convinced. So let's choose one that's even closer to 2, 2.01. Okay, now 2.01 corresponding function value for 2.01 is 4.0. Okay, now we get closer. We can now see. Okay, so it's 0.3. It's 0.3, not 1. 0.3, not 1. Okay, now we're getting closer now to 4 on the right. We can now starting to see that, okay, it's approaching 4, but we still need to be convinced. So let's get even closer. We need to be convinced. To be convinced, we need to see 4.000 something. The zero, we must see that the zeros are increasing after the decimal, after 4. So let's look at 2.00. We can choose 2.001, but we can also choose 2.005. Okay, but it's still going to give us the same similar result. But we can see, okay, now we get 4.015025. Okay, 5025. Now, as you can see here, I'm using this example from the textbook, and in the textbook, this is the numbers they choose. But you can choose different numbers to get that are closer to 2 from the right. You can choose 2.01, 2.001, 2.000. You can keep on increasing the knots, and you'll see that the function is approaching 4. In the textbook, they start at 3, and they keep getting closer and closer to 2. They start, they start far. If you start at 3 and you get closer to 2 from 3 from the right, you're starting far. You can start at 2.01 and just keep increasing. You can say 2.01, 2.001, 2.0001. You can keep on increasing the zeros. You see that the function is approaching 4. And so let's choose the next one. Let's choose 2.001. This is of course the x values that they choose in the textbook. So we just go in the textbook. But again, you can see that your zeros increase. They keep increasing after the decimal, after the 4, to show you that the function values indeed are approaching 4. So that's, then we see clearly that, okay, over here, as we are approaching 2, as the x values are approaching 2, the function values are also approaching, the function values are approaching 4. So as the x values approach 2, the function values also approach 4. But we're doing it now from the right. Okay, so basically the limit of the function when x approaches 2 from the right is simply just equal to 4. It's simply equal to 4. So therefore, this is called the right-hand limit. Okay, this is called the right-hand limit. This is called, so we call this, or this is called the right, this is called the right-hand limit. This is called the right-hand limit. So if you're approaching from the left, that's the left-hand limit. Approaching from the right is the right-hand limit. That's what we call this. And now if the left-hand limit, okay, if the left-hand limit and the right-hand limit exists, like in this case, and is equal to the same thing, right? Then we say that the overall limit is equal to the same thing. What I mean is this. Let's go to the next page. I'll state it like this. I'm going to say this. Now, since the limit of this function, and this function, of course, is x squared minus x plus 2. Okay. Since the limit of this function, when x approaches the number 2 from the left, since it's equal to the limit of the same function, x squared minus x plus 2, when x approaches 2 from the right, is equal to 4. In this case, it's equal to 4. What I'm basically saying here is that since the left-hand limit of this function is equal to the right-hand limit of this function, since that's the case, we can say then, the overall limit, which is expressed as follows, which is the limit. You can call it the overall limit, or you can call it the total limit. Okay, it's called by different names. So you can say the total limit, which is basically the limit of the same function when x approaches the same number, but from both sides now. So the way we write the total limit is we say x is approaching 2, and we don't put minus or plus here because it's the total limit. It represents both sides, and it's equal to the same number, which is 4. So since the left-hand limit is equal to the right-hand limit, the total limit is also equal to that number. In this case, it's 4. So since the left-hand limit is equal to the right-hand limit is equal to 4 in this case, then the total limit is also equal to 4. Okay? And you do get situations where, for a function where the left-hand limit is not the same as the right-hand limit. You do get those situations. So you can get that. You do also get a situation where a function, its left-hand limit is not the same as the right-hand limit. And in that case, the total limit will not then exist. Let's look at such an example. Let's do the next example. Okay, so example 2. Just give me a second there. Okay, so guys, let's do an example now where we look at a function. Okay, let's look at this function here. Okay, let me just find the function. Let's go, let's see this function here. This one here. Okay, so let's look at this example here. Suppose now that you have this function here, h of t. Function is h of t is a piecewise function. You've got h of t is equal to 0 when the t values are less than 0, and it's equal to 1 when the t values are bigger or equal to 0. So it's a piecewise function. If you want to sketch the function, it will look like this. Okay, where this is the function axis, or the vertical axis, and that's the horizontal axis, and that's 0 here. So I'm going to draw the function in purple. Okay, suppose this is 1 here. Suppose here this is 1. Okay, that's 0, that's 1. I'm going to draw the function in purple. Let me choose the color purple. Let's go find the color purple. So guys, this function will basically look like this. Okay, on the left side is going to be flat. It's going to be right on the axis. On the left side, it's going to be flat. It's going to be right on the axis. On the left side, it's going to be flat. It's going to be right on the axis. Okay, right on the axis, because it's 0. Because on the t-axis, the function is 0, and along the t-axis, the vertical axis obviously is 0. So that's basically the function on the t-axis. And for that's what the function is for values that are less than, for values of t that are less than 0. And for values of t that are bigger than 0, the function takes this form. It's a straight line. It's a flat line again. It's a flat line again, but now it cuts. It doesn't cut. It basically okay, but we must make sure that we are very careful here. The function is flat. Okay, let's go to the left again. The function is flat. It's on the t-axis to show that it's 0. Okay, and over here in the middle here, we have a circle. That is there's a circle, and the circle obviously is okay. Let's make sure that the circle is an open circle. So in the middle here we have an open circle, and that open circle basically shows that at 0 the function is not 0. So let me just indicate the open circle in this way. I'll just indicate it by just drawing a circle here. I'll just draw a circle. That's the open circle. So in the middle here, we have an open circle to show that, let me not, okay, let's just leave it like that. So in the middle here, we have an open circle. And over here, the circle is solid. We have a solid circle to show that the function at 0, for t is equal to 0, the function is 1. So for t is 0, the function is 1. And for t values that are also bigger than 0, it stays 1. That's why there's a straight line here that is parallel to the t-axis, and that is that is basically 1. Okay, parallel to the x-axis and cuts 1. I'm sorry, parallel to the t-axis and is intersects at 1. So that's the function. It looks like this when you draw it, and it looks like this when you define it. It's a piecewise function. And now what happens for this function? What if now you want to find the left-hand limit for this function? What is the left-hand limit for this function? Let's say you want to find the limit. What's the limit of this function h of t? What's the limit of this function h of t? when t approaches 0 from the left. So if you look at the left of 0, the function is 0. So if you're approaching t, sorry, if t is approaching 0 from the left, obviously the function itself is approaching 0, because for all t values that are less than 0 or that are to the left of 0, the function is 0. So therefore, because of that, okay, sorry, let me just fix this. Something is wrong with my mouse. Okay, I need to fix my, okay, there we go. So obviously now, because of that, because the function is 0 for all t values that are less than 0, meaning all t values that are to the left of 0, the function then, when the t values are approaching 0 from the left, the function will also approach 0. That's the left-hand limit of the function. So the left-hand limit of the function is 0. How about the right-hand limit of this function? Well, what about the limit of this function, h of t, when the t values are approaching 0 from the right? The t values are approaching 0 from the right. What happens in that case? Again, if you look at the function for t values that are to the right of 0, meaning that are bigger than 0, you can see the function is always 1. It's constant. It's just 1. So therefore, if the function is approaching, if the t values are approaching 0 from the right, if the t values are approaching 0 from the right, then the function will just approach 1 because it's constant. It's just 1. So therefore, the left-hand limit of this function is 0, and the right-hand limit of this function is 1, and they are not equal. So the left-hand limit and the right-hand limit of this function are not the same. So meaning that the total limit of this function does not exist. If the left-hand limit of the function is different from the right-hand limit, then the total limit doesn't exist. So we say, therefore, the total limit, which is the total limit of the function h of t, when t approaches 0, that's the total limit. And you see that it's the total limit because there's no plus or minus to the top right of 0. So that's the total limit. So we say that the total limit then does not exist. Okay, does not exist. And the reason for this is because the left-hand limit is different from the right-hand limit of this function. So therefore, the total limit of this function does not exist. You see? And it's as simple as that. So now what I want to do now, guys, I want to give you guys exercises on this. I want to give you guys exercises on this. Okay, let me give you guys exercises on this. Let me see. Okay, so what we're doing here, I want you guys to calculate limits using table. So for this exercise, you're going to use a table. Okay, so let's go to the exercise. Let's find it. So I want you guys to practice this. Okay. And let's go to the following exercise. I want you guys to practice this. Okay, I want you guys to practice this. So let's go to exercises. I want you guys to practice this. Let's go to exercises. Let's go to the following exercises. Okay, let me go back. Where are these exercises? How can I find them? Oh, here we go. I want you guys to do exercise 11. This is about exercises 2.2. I want you guys to go to exercises 2.2. So please go to exercises 2.2. And I want you guys to do the following there. And this is, of course, let me see what page this is on. This is on page 108. So this exercise is on page 108. So this is on page 108. Go to page 108 and do the following numbers. Number 11 of that exercise, you do number 11, number 12. So please do number 11, do number 12, do number 13, and number 14. So 11, 12, 13, 14 to practice this work. So go and do those ones. And when it comes to choosing your t values or your x values, you can choose your own values. So you don't have to use the values that they give you in the textbook. If you look at the textbook, that's the James Stewart textbook. If you look at that textbook on exercise 2.2, page 108, you'll find that they give you the numbers. They give you the numbers to substitute into the function. Like, for example, the number 11, they give you x is 0.2, 0.4, 0.6, 0.8, 0.9, and so forth. They give you for the left side and the right side, but you can use your own numbers. You can use your own x values or t values, depending on the variable. You can use your own numbers to calculate the limit of these functions. So please, guys, go ahead and do the exercise. I'm gonna post another lecture on limits. I will post another lecture on limits. For this lecture, I'll leave it there, but I will post another lecture on limits later on this week. So I'll post another lecture on limits. Okay, I'll post another lecture on limits on Thursday. On Thursday this week, I'll post another lecture on limits. Okay, so please work on this. Okay, let's stop there. Thank you.